All right. So my name is Guosheng Yin. I'm from University of Hong Kong. I'm going to be the first speaker today. I would like to thank the Royal Statistical Society for giving me this opportunity to share with you some of my work I published last year in Applied Statistics. So it's about a two-stage adaptive randomization for delayed response. In clinical trials, we typically try to compare multiple treatments, and the goal is to identify the superior treatment quickly, as well as treating patients effectively. To achieve this goal, typically people use equal randomization, which is a simple and efficient way to allocate patients randomly. Well, recently there has been a lot of work conducted about the response adaptive randomization. We try to assign more patients to better treatments based on the information accumulated in the trial. Well, before you can implement adaptive randomization, typically a pre-run of equal randomization is used because you want to stabilize the parameter estimates before you apply the real-time adaptive randomization. But the question is, it's not clear how many subjects you need for this ER stage, equal randomization stage. And typically, in practice, it's also often chosen arbitrarily. So that's one question I'm going to address. So when we talk about adaptive randomization, there has been a long history. It can be traced back in 1933, and also there play the winner rule, randomized version of the play the winner rule, and there are also some Bayesian adaptive randomization procedures and banded problems. So I want to just illustrate adaptive randomization using the play the winner rule. So it's very simple algorithm. Basically, suppose you have treatment A and treatment B. So if you treat a patient using treatment A, and if you observe success, then you continue using this treatment for the next patient. And until you observe a failure, then you would switch to the other treatment. Then you continue in this way until you observe another failure, then you would switch. So the play the winner rule actually has a definitive switching if you observe failure. So later on, people thought about it. Why don't you use a randomized play the winner rule? So instead of a definitive switch, you can view the randomized play the winner rule as the urn model. So basically you have an urn with ball A and ball B. If you observe a response, then you would add more ball A. Suppose the treatment is ball A, then you would add more ball marked with A. So the next time when you draw another ball, you would have a higher chance to draw this ball A. So that's the randomized play the winner rule. So recently there has been another class of adaptive randomization which trying to target an optimal allocation ratio. So one way is to minimize the variance, which is also equivalent to maximize power. And another way proposed by Rosenberg and other authors in 2001, so we're trying to minimize the number of non-responders in the trial. So just give you an example, suppose we consider a two-arm trial with binary data. So P1 and P2 denote the response rate for treatment 1 and treatment 2. So if you minimize the variance of the difference between P1 head and P2 head, then the allocation ratio would be given by this quantity right here, which is also called Neyman's allocation. So on the other hand, if you try to minimize the number of non-responders while you're fixing the variance, then the allocation ratio has a very simple form, the square root P1 over square root P2. So this is for binary data. How about continuous data? For continuous data, suppose you have mu1 and mu2 denote the means of the normal distribution, and sigma 1 square and sigma 2 square are the corresponding variances. So the Neyman allocation ratio actually is very simple, just the ratio of the two standard deviations, which actually minimize the variance. If you look at this ratio, actually, typically we assume sigma 1 equal to sigma 2. So that's the reason why we typically use one-to-one allocation, which actually corresponds to Neyman's allocation, because sigma 1 is assumed to be equal to sigma 2. On the other hand, if you try to minimize the total expected response, I mean, here, what I mean by response is a lower outcome is better. For example, for blood pressure drug, you want to lower patient's blood pressure. So if you try to minimize the expected response, then you will have this allocation ratio. So now let me talk about a little bit about the Bayesian adaptive randomization. So in the Bayesian approach, actually, we can assign patients based on this posterior probability. So lambda is the probability of P1 greater than P2 given the data. So Y1, Y2 representing the accumulated data in the two arms. So we compare this posterior distribution with P1 and P2. Actually, there's an advantage because it automatically accounts for both the point and variance estimates of the response rate. So here I use a figure to show you the point. So if you look at this figure, on the left is early stage. Basically, at the beginning of the trial, you don't have much data. So you basically have a two posterior distribution that are largely overlapping. Because the data is very sparse at the beginning of the trial, so the posterior distribution actually is quite flat. But in the later stage of the trial, you have accumulated a lot of information about the two drugs. So the posterior distribution is getting sharper and sharper, and actually by comparing the posterior distribution, not only you consider the posterior mean, you also consider the posterior variance. So you can see the two distributions on the right side panel actually being separated out much more clearly than the early stage. So that's one advantage of using Bayesian adaptive randomization. Actually, you can even explore a more flexible class of randomization probability by introducing a power transformation parameter, gamma. And you can also let this gamma depend on the accumulating sample size. Small n is accumulating sample size, and n is the total sample size. So basically, it's sort of like a box-Cox transformation in some sense, and you can explore a more class of randomization probability. So now let me switch the gear, talk about the delayed response, because this is very common in clinical trials. So let me show you this plot. Suppose you have an assessment period called TAL. So this TAL basically is the assessment period to evaluate the outcome or the response of the patient. So basically, TAL equals 6A. A basically is a curve, let's imagine A equals 1. So every week, there is one cohort of patients enter the trial. So you look at this cohort 1, there are 4 subjects, and they are being treated. So you follow them, and then you saw that the second subject actually responded. You see a cross that basically you saw the outcome. So the patient responded. But the first subject and the third and fourth subject, I put a circle there. Their outcome has not been fully evaluated yet because by the next week, cohort 2 arrives, and those 4 subjects are ready for the treatment. But by that time, the 3 patients in cohort 1, they are only partially followed, and their efficacy outcome have not been observed yet. So that poses the missing data problem, or you can also consider as a censoring problem. So that's basically called a delayed response, or sometimes people call it a late onset outcome problem. So that's basically like a missing data or censoring data. So for this kind of censoring data, people have done extensive work about time to event data analysis. So you can consider a survival model. So let's suppose T follows the exponential model, which has a survival function given by ST. And based on this simple exponential model, we can also minimize the total expected hazard. Okay, because in survival analysis, hazard is typically what we care about. We try to minimize the total expected hazard while fixing the variance of the theta hat 1 minus theta hat 2, so that you can also obtain optimal ratio, allocation ratio I call R theta here. So that's what people have done using time to event skills. Well, you can also consider using the survival function. So typically, we would think the patient's response as a good event, and if patient as a responder is good event. So the sooner the patient experiences the event, the better. So we can minimize the total number of patients who have not responded within the assessment window 0 to 12. So we can derive an optimal allocation ratio by minimizing this quantity. Basically, it's N1 times S1 plus N2 times S2, subject to fixing the variance as a constant. So we can get another allocation ratio. And the next feature about this allocation ratio is if the sample size is large, if P1, P2 are small, then this RS reduces to the binary case. And the binary case is what we have seen on the earlier slide, which is square root P1 over square root P2. So now let me talk about the two-stage response adaptive randomization. Now let's consider a two-arm trial, very simple setup. This binary endpoint, Y1 and Y2 are the newly random variables with P1, P2. So the hypothesis is P1 equals P2. And the first question I'm trying to address is, when do we switch to AR? Because we know the trial starts from ER, but the question is, when we switch to AR? So to solve this problem, let's consider, suppose we have n patients in each arm. Then we can construct a likelihood ratio test of statistics called TM, and this is very standard likelihood ratio test of statistics. So under the null hypothesis, the likelihood ratio test of statistics follow a chi-square distribution with 1 degree of freedom, and then we can compute this TM hat by plugging in the MLE of P1 and P2, because P1 and P2 are unknown parameters, and the rejection region, which actually I put two quotes there, because I'm not going to reject the null hypothesis or whatsoever. I'm only using this as the criteria whether I'm going to switch to AR or not. So if T hat is greater than this chi-square critical constant, then I'm going to consider, I'm going to sort of like reject the null so I can switch to AR. So that's the idea. So what is the role of alpha tilde? Alpha tilde actually is the threshold level for switching from ER to AR. Typically, alpha tilde should be greater than the 12th Kaplan error rate alpha. So the nice feature about this setup is, if the treatment difference is large, then the sample size for the equal randomization, which is denoted by NE, would be small, so that the trial can move on to AR quickly. Well, on the other hand, if the treatment difference is small, then NE would be large, because if the treatment difference is very small, so there's not much difference between ER or AR, because P1 and P2 are so close, whether you do equal randomization or adaptive randomization wouldn't make much sense, wouldn't make much difference. By controlling alpha tilde, the two-stage design can automatically adapt to the true difference between P1 and P2. But think about it, on the other hand, if we fix the sample size NE in the ER stage, it would not be adjustable to the treatment difference, right? It doesn't matter how different this P1 and P2 are, you will use the same sample size for the equal randomization stage. So that's the difference between if you're using alpha tilde as a threshold to control the equal randomization sample size. So the two-stage procedure goes like this. So in stage 1, the trial begins with equal randomization, and we are going to continuously update this likelihood ratio test statistic after enrolling every new patient. If T hat is smaller than the critical constant, then we continue using equal randomization. Otherwise, we switch to AR stage. That's stage 2. So in stage 2, we start to implement response adaptive randomization, and you can either use name allocation or you use this square root P1 over square root P2 to minimize the number of responders. So the idea is very simple. We simply apply this kind of likelihood ratio test, trying to examine how different the two arms are. Now let me talk about how to solve the problem of delayed response. So as I showed you earlier, delayed response actually basically is related to missing or censoring outcomes. That poses immense difficulties when we apply AR in the real-time trial conduct. But if you view the efficacy endpoint as an event of interest, we can model the time to efficacy using the Kaplan-Meier estimator. Actually, the Kaplan-Meier estimator has another formulation, which is called redistribution to the right. So basically, you can fractionize the censored observation based on the patient's exposure time in the trial. So you can redistribute some of the point mass from the censored observation to the right. To the right, you can consider it to infinity. So typically, a drug's related efficacy event is evaluated between 0 and tau. So y takes value 0 or 1, depending whether the subject has responded or has not responded within this assessment window. So more specifically, let's let T denote the time to the event of efficacy, and U denote the actual follow-up time for the subject. So the subject's response is censored if the subject has not responded and also has not been fully followed up to tau. So if you look at the bottom figure here, basically you have a subject who is censored at UI, but who is possibly experienced the event between UI and tau. But we don't know that, right? So if we observe a censored event before tau, then the efficacy has not occurred yet. We can obtain a fractional one as a contribution to the censored observation to the response probability. So in fact, we can, using this idea of redistribution to the right, and we can calculate this conditional probability. So given the subject has survived up to time UI, and what is the probability that this subject will experience the event between UI and tau, so that we can plug in the Kaplan-Meier estimator, which is as had into this formula, and we can easily calculate the fractional contribution for censored observation. So now we have a new outcome variable called R. So R can take value 0 if the subject does not respond. Takes value 1 if the subject has responded. Takes the value of Y hat. Y hat must lie between 0 and 1 if the response of the subject is censored. So now we basically account for all the possible scenarios for outcome. So now let me show you some of the numerical study I have done. So I'm going to consider a simple 2-arm trial with binary outcome, trying to investigate the 2-stage fractional AR design. So the assessment period for efficacy is 12 weeks, tau equals 12 weeks. And the cool time interval between every 2 consecutive cohorts is 1 week. That means every week there is a new cohort of 4 patients who enter the trial. And the sample size was calculated based on type 1 and type 2 error rates. And we fixed the threshold level for ER and AR switching alpha tilde at 0.3, and we replicated 10,000 trials. So here's the distribution I want to show you that's from which we simulated the data. So we use the Weibull distribution to simulate the time to event data. If you look at this solid curve and also a dashed curve, the solid curve corresponds to arm 1 and dashed curve corresponds to arm 2. So by week 12, if you see week 12, then you see the response rate for arm 2 actually is 0.2, and the response rate for arm 1 is 0.4. But you notice that these 2 curves are quite different by using different shape and scale parameters. Particularly, this dashed curve is higher than the solid curve before week 10. And that would cause some problem if you consider the delayed response. I'm going to show you in a minute. So we are going to compare 3 methods. The first method is complete data AR. So complete data AR means I'm going to follow every subject till the occurrence of response or the end of the follow-up period before I randomize each new patient. So basically, there's no missing data, there's no censoring. I'm going to follow every subject to evaluate it, to fully evaluate its outcome. So that's basically the benchmark for comparison. That's the best you can do. And the second method called fractional AR is what we have proposed. Basically, we consider those outcomes that's being censored as time to event data, and then we use the redistribution to the right scheme to calculate the fractional contribution of the censored observation. So that when a new subject enters the trial, this subject can be immediately randomized upon arrival. The third method we consider is observed data AR. The observed data AR basically, you only use the observed efficacy data only, while you treat censored outcome as non-responder. So, for example, if the subject being censored, by the time you have not observed a response yet, you basically consider that's non-responder. So it's kind of a naive method. You basically treat those censored observations as non-responder. But that's obviously wrong, because even though the subject has not responded by the time you are evaluating, you are trying to assign the next cohort of patients, this subject could possibly respond later on during the follow-up. So that's the kind of naive method we want to compare, and which actually is the current practice of many this kind of delayed response trial being conducted. So I want to show you this numerical results in this table. So if you look at it, I'm going to fix P2 at 0.2, so that's arm 2's response rate at 0.2, and this is sample size. And I'm going to let P1 be from 0.2 up to 0.8. And you observe that we have three methods in comparison. And if you look at the first three rows, so the first one is observed data AR. So the observed data AR actually allocated 47.4% of patients to arm 1, while the other two methods roughly equal allocation, which is true because for the first case, I'm considering P1 equals P2 equals 0.2. So there's no difference between the two arms. Regardless you do equal randomization or adaptive randomization, you should have exactly 1-to-1 allocation. But you see the observed data AR actually mistakenly think arm 2 is the better treatment. The reason is, if you remember, if I go back to the previous slide, if you remember this plot, you see arm 2 actually have a higher response rate at the beginning of the follow-up. Up to week 10, it has a higher response rate. So that's the reason if you use observed data AR, you in fact would allocate fewer subjects to arm 1 because you think arm 2 is better, which actually is wrong. So that's one thing I want to show you. And if you look at the second row, which is complete data AR design, actually if you look at the last two columns, the trial duration, because it's complete data design, so you have to follow every subject to the full extent, either up to 12 weeks or you follow the patient until the response being observed. So by doing so, actually the trial duration is very long. It's over 6 years. But if you look at the third row, the fractional design, we did not prolong the trial time. It's still like about a year. Well, we basically have all the similar allocation percentage as the complete data is about 50%. The allocation standard deviation is similar. The number of responders are similar too. So that's one thing I want to emphasize. If you look at the last three rows, so P2 equals 0.8, then you look at the allocation percentage to arm 1. You see the number in red. Basically, again, this is happening because the observed data thinks arm 2 is better. Okay, that's why. There's a difference. We have a 65% allocated to arm 1, but we only have 60% allocated to arm 1 if you use observed data. That's also for the same reason. And if you look at the number of responders, if you use complete data or fractional AR design, you have about 3 more patients being responders than the observed data design. And if you look at the last column corresponds to equal randomization. So this is very interesting. If you have P2 is much larger than P1. For example, P1 is 0.8 and P2 is 0.2. So the sample size for equal randomization actually is much smaller. So if you look from the top to the bottom of the last column, you see this NE keep decreasing. The reason is as the difference between P1 and P2 are getting larger and larger, the trial can quickly identify the difference between the two arms, so it can switch to AR very quickly. So basically, that's the interpretation of the table. Basically, the observed data AR design falsely assign more patients to arm 2 because of the Weibull distribution. You have seen that before week 10, arm 2 actually has a higher response rate. But in fact, a lot of patients in arm 1 actually they responded later between week 10 and week 12. So that's another set of interpretations. So basically for P1 equals 0.8, the fractional AR increased the number of responders by more than 3 patients over the observed data. And the last point is the trial time was dramatically reduced from 370 weeks to 53 weeks. So by using a fractional design, actually, you are not going to prolong the trial time. So here's the conclusion of my work. So basically, we studied this two-stage fractional design. We try to address 2 practical issues for response to data randomization. First is how to determine the number of patients in the ER stage. So we basically use the likelihood ratio test statistic, try to see whether there's a difference between P1 and P2. The second issue we try to address is what if the patient's response cannot be observed quickly for the real-time adaptive randomization, so their possibility of delayed response? Then how can you use this redistribution to the right, consider the missing data as a censored data, and using their fractional point methods to calculate the response rate. And the non-parametric fraction design actually is very robust and easy to implement because it only uses the Kaplan-Meier estimator. And the Kaplan-Meier estimator is a standard method and can be implemented in most of the statistical softwares. So the last point is we use the likelihood ratio test using alpha tilde, where alpha tilde is not really for hypothesis testing. It simply serves as a venue to decide whether we are going to switch from ER to AR. So it's not about formal hypothesis testing. We are going to reject the null or whatsoever. So here are the main references. And the first paper is what we published last year, and that talk is based on. And I would like to thank all the audience who have been participating in this webinar. Thank you very much.
Okay. So my name is now Franz Koenig, and I will present the next presentation, which is on adaptive graph-based multiple testing procedure, which is a joint work with my colleagues Florian Klinglmueller and Martin Posch. And we would like to thank the PSI and also the Royal Statistical Society for giving us the opportunity to present our paper to you today. So, we know that in the recent years many modern, sexy multiplicity testing procedures have been suggested in the statistical literature, and many of these multiple testing procedures allow to address multiplicity issues in clinical trials, so very complex issues, and they also reflect the contextual relationship between hypotheses in the inference procedure. For example, like pointed out by Bob O'Neill at many occasions, you shouldn't test a secondary hypothesis if the corresponding primary hypothesis hasn't been rejected before. So you all know this name, like fixed sequence test, fallback test, gatekeeping test. And Also, graphical methods have attracted a lot of attention, so this graph-based multiple testing procedures, because it really helps you to tailor your multiple testing procedure to the problem at hand. It makes the guiding principle behind the procedure more transparent, which will help you to communicate the procedure more easily to clinicians, to ethics committees, or to regulatory authorities. What about multiple testing in adaptive designs? There are also many publications, but interestingly, methods have been suggested for a limited number of standard situations. So we have many publications on many wrong comparisons with treatment selection, for multiple co-primary endpoints, or for subgroup selection. But the mix of primary, secondary, and more treatment groups, there's still a lack. So these papers just reflect only very simple relations between hypotheses, and it's quite difficult or almost impossible to tailor to more general multiple testing procedures. And for example, if you would use the closed test together with the adaptive combination test, it does not allow you to use the classical fixed sample analysis if no adaptations are performed. And somehow it would be nice if you don't adapt anything during your interim analysis, that you can simply run your usual SAS code and perform the analysis like you would do in a fixed sample design. So now I'm on slide 4. What about on multiplicity in adaptive design? So in 2014 we published a paper where we reviewed 59 scientific advice procedures of the European Medicines Agency, and there we realized that many people would like to perform adaptations and adaptive designs. However, there are really some concerns with the type of error rate, especially, for example, in clinical trials where you want to compare more than one treatment groups against the control group. And the typical argumentation, which is wrong, used by some of the sponsors was, at the interim analysis, we only want to select one treatment group out of 2 or 3, and as we don't perform any testing at the interim analysis, we would like to use the full level alpha at the end. However, as we know, that's not possible. So today, I would like to present you multiple testing procedures for adaptive design that reflect the contextual relationship between hypotheses, and only quite recently you can find some statistical papers in statistical journals. So, for example, there's a very nice work by Jiajing Yin and colleagues on adaptive designs for primary and secondary hypotheses. Toshi Subitani, he extended the graph-based method by Plates et al. To adaptive combination test. But the topic of my talk today is I would like to show adaptive graph-based multiple testing procedures based on the partial conditional error rate. And this paper has been published in the Journal of Pharmaceutical Statistics last year. And if you go to the journal webpage, you can access it for free there. So I'm now on slide number 6. So what are adaptive graph-based multiple testing procedures? They are a very general framework to address multiplicity in very complex clinical trials. They reflect the relative importances, the contextual relations, logical restrictions of clinical hypotheses, and they permit adaptive interim analysis. So this means you can perform trial modification using unblinded data or any external information, and you will, with this method, you will enforce strict control of the type 1 error rate. And to do so, we have combined 2 methods. So to deal with multiplicity, we simply apply the graphical approach, which was published by Frank Pretz, Willy Maurer, and Werner Brannert and Martin Posch in 2009. And to account for adaptivity, we use the partial conditional error, which I will explain later on. So first, let me explain the graph-based multiple methods, and I will illustrate it on one example, which I will use throughout the remainder of my talk. So we have a trial with multiple treatment arms, and we're interested in testing multiple endpoints. So it's, let's say, a phase 3 clinical trial, and we have two treatments, T1 and T2. So let's say T2 is the higher dose, T1 is the lower dose, and each dose should be individually be compared to placebo. And we have two endpoints, so primary and a secondary endpoints, which means at the end of the day we would like to test 4 null hypotheses, so the primary and secondary endpoint for the low dose and the primary and the secondary endpoint for the higher dose. So what are the desired properties for our multiple testing procedure? Clearly, as it is a phase 3 trial, we would like to control the family-wise error, let's say at an alpha of 2.5, one-sided. Then, when we assume equal effect sizes, both treatments should have equal chances to be rejected at the end. And we would like to test a secondary hypothesis for a specific dose only if the corresponding primary hypothesis is rejected. And last but not least, we would like to reject as many hypotheses as possible. So I'm now on slide 7, and I will move to the next slide. So please click. So now you can see how you can visualize the multiple testing procedure we are interested in. Now, in the lines you can see we have the primary and the secondary endpoint, and we have one column for treatment 1 and one for treatment 2, and now each node should correspond to a specific null hypothesis. So H1 is the primary endpoint for the low dose T1, H3 is the null hypothesis for the secondary endpoint for the lower dose, and so on. As said before, we would like to assume equal effect sizes, and when we assume equal effect sizes, both treatments should have equal chances of a positive result. So what we can do is we split alpha equally between the two doses. And as we also said, we don't want to test the secondary when the primary has not been rejected. We give initially 0 weight to the secondary endpoints. And now if you look at the notes, you see we have split the alpha between H1 and H2, and no alpha is given to the null hypothesis of the secondary endpoints. Now I click again. Now, if a null hypothesis is rejected, we would like to reallocate the weight from the primary to the secondary endpoint, and this is now indicated by the edge, which goes, for example, from H1 to H3 or from H2 to H4. So this should indicate that as soon as the specific null hypothesis is rejected, we will give all the alpha to the next hypothesis. And as said before, we would also like to we also wish to reject as many null hypotheses as possible. So you can see if for one dose we have rejected both null hypotheses, we move the alpha over to the next dose, which is indicated, for example, by the edge going from H3 to H2, or the edge from H4 to H1. Now let me give you a very quick numeric example. So now you can see the p-values for these 4 null hypotheses in this box. So P1 is 0.012 and so on. And now, how do we know which null hypothesis can be rejected? Simply we look if one of these p-value falls below its levels, and we can see P1 is below alpha over 2, so we can reject already H1. This is now indicated by the red color. So as H1 has been rejected, we remove it and we move all the alpha to H3. And H1 can already be deleted from the graph. So now we look and we see, P3, it's also smaller than alpha over 2. So 0.009 is smaller than 2.5 divided by 2. So we can also reject H3. We remove it, and now all the alpha is moved to those two, which means now we can test H2, so the primary endpoint for the higher dose at the full level alpha, and we see the p-value is 0.024, which is smaller than 0.025, so we can also reject H2. But unfortunately, we cannot reject the secondary endpoint for the higher dose. Good. So I moved now to slide number 9. You have seen the graphical approach presents really an intuitive way to construct, to communicate, and to run a multiple testing procedure, and it provides strict type-1 control. Why does it provide strict type-1 control? Because in the background, the graph defines a closed testing procedures of weighted Banzeroni tests. So in the background, you have the full closed test, but you don't have to take care how the test for all the intersection hypotheses are defined. So this graph-based method, which is based on the sequential rejection principle, provides you a shortcut to the closed test. So have a look in the paper of Frank and colleagues, where it's really very nicely explained. So what's behind the scene? As said, behind the scene, we use the closure principle. Just to remind you, what's the closure principle? It simply says we can reject an elementary null hypothesis only if we can reject the elementary null hypothesis itself at full level alpha, and all the intersection wedge part in also at full level alpha. So this would require 2 over m minus 1 tests, but you don't have to take care how these tests are defined, because the graph does it automatically to you. And on slide 11, I just show you that for our very simple example where we would like to test 4 elementary null hypotheses, in the background actually 15 intersection hypotheses are tested, and here you can see which test is used for which intersection hypothesis. Now we move onwards to adaptive designs. So adaptive designs, where we would like to change the design. So we start again with a graph, as we would do in a fixed sample design, where we specify our multiple testing procedure for all m hypotheses we would like to start with. And then, that's not so different, at an interim analysis, now we perform adaptations. The adaptations can include, for example, that we look at some of the hypotheses and we realize we are not longer interested in it. For example, those 2 might be toxic, and so we would drop also hypotheses for those 2, or the lower dose does not show an effect and we would like to drop them for futility reasons. Or maybe we underestimated the variance estimate and we would like to increase the sample size. So here we perform the interim analysis, and only for the continued hypothesis further patients will be collected. And in the final test, we would like to use the data of both stages, and also we have performed adaptations. The family-wise error rate should be controlled in the strong sense. So what are natural applications, for example, treatment or subgroup selections, design in clinical trials? I will illustrate the method again for our example, which we have shown before. So, as said, we started with a comparison of 2 doses against the control group. And here again, you see the graph for a multiple testing procedure we started with. And now, midway through, we make an interim analysis. So the trial data are unblended. And let's say due to safety concerns, the board makes a decision to stop treatment arm T2. So the higher dose should be dropped. And our proposal is now, if you drop something, then simply make a new graph where you can build any new graph, including the hypothesis you are interested in after the interim analysis. So here you can see now we dropped the hypothesis H2 and H4 for the higher treatment, and we would only be interested in testing the primary and secondary hypothesis for the lower treatment in a hierarchical way. So there remains the question, what can we do? Which alpha should we put on the primary hypothesis for T1? So having dropped T2, it implicitly means that we have to retain H2 and H4, and a very simple strategy could be we simply discard the alpha foreseen initially for the higher dose, which means we would then test H1 and H3 using a fixed sequence test, a hierarchical test at alpha over 2. As you will have immediately noticed, this is a very conservative procedure, but a valid procedure. But we simply don't use the alpha originally foreseen for the higher dose, and this procedure does not allow further adaptations. So, for example, we cannot change the sample size. So there's the question, can we do better? So what's our desired strategy? We would like to use the first stage data from the drop dose. Optionally, maybe we would like to also reallocate the sample sizes foreseen for the higher dose to the lower dose and the control group. And we would like to use the updated graph to define a new test procedure. Again, I show you now the table where you can see all the tests for the intersection hypothesis. So here in the second column, you see the original test for the fixed sample design with also an interim analysis, and the simple strategy is where we dropped the hypothesis for the higher dose. And for example, if you compare it, we see that half of the alpha is not used, and we also don't use the already collected data for the higher dose. So can we use the first stage data from the dropped treatment when testing the corresponding intersection? And I will illustrate it now for the intersection of all four hypotheses. So how can we define an adaptive test instead of the simple strategy? And one way to introduce such flexibility is the conditional error, which was suggested by Müller and Schäfer. What is the conditional error? It says at the second stage, so after you have performed an interim analysis, use only the independent second stage data. And what's the significance level? The significance level is a condition level, which is defined here, and it's the condition level, so it's the probability under the null hypothesis that you would reject the corresponding null hypothesis conditionally on the data observed so far. So if at the interim analysis your data would be very promising, the condition level would be higher. If it's not very promising, it would be lower. And Müller and Schäfer have shown if you apply this principle, you will always achieve strict type 1 error control. However, there's one caveat. For multiple hypotheses, one would need to know the joint conditional distribution of second stage statistics, which in general is unknown. For example, if you have only a single endpoint and you're in the many-one comparison setting, then we would know the correlation. Then there exist some solutions. For example, we have published an adaptive version of the Planet test in 2008. However, for example, if you test more than one endpoints, you usually don't know the correlation structure between the endpoints. And then you cannot apply the conditional error rate directly. And therefore, instead, you use the partial conditional error. And the second stage test then is based on independent second stage observation at the conditional level, where we simply take the conditional error of each hypothesis separately. So we don't need to know the correlation structure, and for a specific intersection, it's always the sum of the marginal conditional errors involved. So for this method, you don't need to know the correlation structure between the hypotheses. And now you can see the table how our graph-based method would define the test in the background. And what you now will immediately realize is that the adaptive test is always equal or more powerful than the simple strategy, because you could also derive for the simple strategy the conditional error, and you see for the adaptive one, the conditional second stage label are always equal or higher, which means we must have a higher power for the adaptive strategy. So, what are now the adaptive graph-based multiple testing procedures? Let's wrap up. It means in the planning phase of the trial, we define a pre-planned test using the graphical approach. At the interim analysis, we can perform adaptations based on any internal or external data, so we can drop treatments, we can reassess the sample size. We have full flexibility because no specific selection rule nor the number of hypotheses to be selected needs to be pre-specified. And if at the interim analysis you want to change something, then simply draw a new graph. So use an updated graph to derive the suitable second stage multiple testing procedures. So you can remove nodes of the dropped weights. You can also reshuffle the weights. And the really nice thing is, if no adaptations are performed, then you can run the graph-based multiple testing procedures as originally planned. So there's no price has to be paid for the option to perform an adaptation. And the use of the conditional error principle ensures that the family-wise error rate will be controlled in the strong sense. Now I will end up with a small simulation study just to show you whether it's worth all the effort. So we will stick to our example where we compare two treatments against a control group with the two endpoints. Now in the simulations, I will assume a common non-standard deviation of sigma equals 1. And the lower dose T1 has always half of the effect of the higher dose, and we assume equal effect sizes in either endpoints, and the total sample size per treatment arm should be 80, and now we perform an interim analysis halfway through, and as discussed before, now we say in the interim analysis the data safety board decides to drop T2, and we will compare now three different valid test procedures. So it's a simple one, which means, okay, we drop H2 and H4. However, we then can only test H1 and H3 at the originally foreseen level of alpha over 2. The second one is where we use the adaptive graph-based method we suggest, and the third option, which is leveled by 82, it's also our adaptive test, and in addition we perform another adaptations. We say, okay, the 40 patients which are originally were foreseen for the higher dose are now reallocated to the lower dose and the control dose, control group. And here you can see the simulations results. So on the x-axis, you can see the true effect of the low dose. As said, here we just assumed that both the primary and the secondary endpoint has the same efficacy. And now the black solid line is the power curve for the simple strategy, and you see with the adaptive one we have a much higher power. It's a red solid line. The red solid line is the power for the primary endpoint of the lower dose using our method. And if you would also reallocate the sample size, then you have a huge gaining power. It's a solid green line, and the dashed lines are simply the power curves for the secondary endpoints for the respective testing strategy. So you can see, in comparison to the simple naive testing procedure, the adaptive graph-based version really improves your power simply because in the background we use the first stage data to test some of the intersection hypotheses involved. So our approach is suitable for any general graphical procedure. You might use it for treatment selection, subgroup selection. You can re-weight the initial significance level being given to the single hypothesis. You can make a change in the priorities. You might do some sample size reassessment, and theoretically the interim analysis may be even unscheduled. Even in such a case, you would have strict control of the type 1 error rate. Here on this slide I show you just some example of more complex multiple testing procedures which are all collected. I'm now on slide number 22 in the package of Cornelius Rohmeyer and Florian Klinglmueller, who have developed an R package which is called GMCP, and as a working version Florian has already included also the adaptive graph-based method. So you can play around with this R package to look how the graph-based or the adaptive graph-based methods work. So let me conclude with my presentation. They are a very intuitive way to design complex multiple testing procedures. They cover a large class of multiple testing procedures. The weighted directed graph completely defines the adaptive multiple testing procedures. It allows flexibility, so you perform design adaptations based on internal and external information, and you don't need any assumptions on the joint distribution of the test statistics. And what's really a nice feature, without adaptation you can perform the classical pre-planned fixed sample test, and you can adjust for multiplicity for different sources, and you will always have strong control of the type 1 error rate. And here some of the references I've shown before, and the presentation was based on reference number 9, so it was published in Pharmaceutical Statistics in 2014. So here I will end and hand over to the Royal Statistical Society again.
Franz, thank you very much, and Guosheng, thank you very much as well. All on the call, my name is Robert Cuff. I'm chairing the question and answer sessions, and so I'd like to ask you, if you want to ask a question over the phone, please use *6 to unmute yourself, and then once you're done asking the question, please do remute yourself again. As everybody knows on these big calls, we do get a problem with background noise if lots of people are unmuted. So please do use *6 to unmute yourself or to remute yourself once you're done asking a question. If you have a difficulty using the phone, or you're not getting through or not able to unmute yourself, you should be able to see on the top of your screen the Q&A functionality that comes with the Global Meet meeting, and so you can ask your questions through that forum as well. So before I'll even use my chair's right to ask a few questions, we've already got one that's come in from the Q&A from Patrick Schlumer. Patrick asks, does the adaptive design from Franz's talk also apply to entangled graphs?
Yes, you could also apply it to that one.
Okay. A quick scan to see if there are any immediate questions that are coming in over the phone lines. Okay, well, first of all, Guosheng, I'd like to ask you, I see your presentation being in two parts. One answers the question that we all face in clinical trials of how to deal with the fact that your patients don't all arrive on the same day, and you have to wait for some of them to turn up and some of them to be observed, and it takes a while to get the response. And the first part is probably where, and that seems, I have no real questions there, but the first part I think I'd like to ask about the choice of the metric that you're using to determine the switch from equal to adaptive randomization. When you characterized that problem at the start, you described the equal randomization phase as a period where you tune the parameters and you gain a certain amount of information before you start to allocate people to one arm or another. And when you presented your methods, it seemed that you weren't waiting for a certain volume of information, you were waiting for a certain size of signal. So I wondered whether that answers the problem, and if not, whether there's a natural generalization to information-based trigger points.
Okay, so basically, I have an alpha tutor, which is the threshold level for switching from ER to AR. So the practical question is often about how large this ER stage should be. When I talk to my colleagues, I used to work at MD Anderson Cancer Center, so I talk to my colleagues or those oncologists, there's unclear answer how many subjects we should allocate to ER stage. And we typically just fix the sample size. We say fix 30% of the total sample size in ER stage, and then 70% would be AR. So we had several trials run like that. Then we try to solve this question, using this kind of hypothesis testing, sort of like hypothesis testing, but in fact, they are not doing any formal rejection. It's not about the rejecting the null hypothesis. We're just using that as a mechanism, trying to switch, make a decision whether you want to switch from ER to AR based on the accumulated information in the trial. And the advantage is that, as I showed in my simulation study, if there's a large difference, then the switch would be very quick because the trial would quickly recognize the difference between P1 and P2 so that you can switch in a much quicker way if you have a large difference between the two treatments. Otherwise, if the two treatments are quite similar, it doesn't matter you switch to AR or not. It's all sort of like equal randomization because P1 is roughly equal to P2. Either you use ER or AR, it doesn't matter. And the reason people want to use ER, as you said, people want to accumulate enough information to stabilize the estimates. Because if your estimates are not being stabilized, if you have a lot of bias, then even using AR doesn't help you. The reason we want to use AR is for the ethical reason. We want to have more patients to be treated by the better treatment arms. So that's basically the whole point. We try to switch from ER to AR because at the beginning of the trial, there's no information about the two treatments. So that's sort of called state of equal points. So there's no information which treatment is better. So the most standard way is just using equal randomization instead of using AR. But as the trial moves on, you collect more information. You basically sort of like figure out which treatment is better. Then you can have a higher probability of assignment to that better treatment. I hope I have answered the question.
No, it's a good answer. And so a follow-up would be, so when you have these discussions with your trialist colleagues and you discuss it, so take the example you used of the trigger of a p-value in the region of about 0.3, and when you talk to them about the kind of hazard ratios you would see that would trigger a switch to adaptive randomization before you're 30% of the way into the study, does that correspond to their intuition about the kind of hazard ratio that would make them think, oh my gosh, we really need to start changing the randomization ratio. There is an ethical case to start making a change to the trial? Do your thresholds match their intuition as to when you need to start moving?
Oh, in terms of the alpha tilde equals 0.3, actually we have done some sensitivity analysis. I didn't have time to show you the numerical results. Actually, we try alpha tilde from 0.1, 0.2, 0.3 up to 0.5. The general principle is we have to make sure alpha tilde is greater than the type of error rate of your trial. So typically we use alpha equals 0.05. That's the type of error rate we try to control. But we don't want alpha tilde to be smaller than that. So that's why you can try alpha tilde 0.4. As what you said, in terms of hazard ratio, so that's a good point. Actually, that's related to like a survival analysis trials. If you have time to event data, you have proportional cost, proportional hazards model, calculate hazard ratio. But in that sense, actually, there's not much difference between time to event analysis or the binary data outcome. You have binary data, you can compare like odds ratio or just the response rate. In terms of survival analysis, you have hazard ratio. So in terms of switching or not, I discussed this with medical colleagues. Actually, they like the idea of switching from ER to AR because all the doctors, they favor in treating their own patients using the better treatment. They're excited about this kind of idea. So I don't see much difference between using hazard ratio or all the odds ratio, all the difference between the log of the response rate. They all fall into the same framework.
Okay. And well, this is a question for you, but it's also a question for Franz, so you're getting advance warning. How far are we away from code that the well-meaning but SAS-addicted statistician working in pharma can use? So how far are we away from code and SAS that people can use to replicate these methods or implement them in their trials?
For the fixed sample setting, you can simply run your SAS code. However, if you perform some adaptations, we don't have any SAS macros yet. That's the bad news.
And for your method, the example that you used to set up your presentation struck me as one of I guess what we would classify as an unplanned change as an interim. Is that where you see the principal advantage of the methods you describe? Is that we can accommodate these adaptations that we didn't pre-specify and guarantee to do from the outset of the study?
I wouldn't say it was not. In some respect, it was the timing of the interim analysis was pre-specified, and also that you would like to look into the data, because if you have a DSMB, you have to decide in advance how the board should look like, at which point you have to look at the data. It would always be good to put some more remarks in the study protocol or in the guidance document for the board, which type of adaptations should make. But sometimes, how real life in clinical trials is, a situation might show up, you haven't thought about it before, and then this is a method which can be still applied, even so the type of adaptation has not been pre-specified. But to increase the trust in the results of the trial, it would always be good to pre-specify as much as possible, if it's a phase 3 pivotal trial.
I heartily endorse that. But as I understand your discussion, you're suggesting that this is a general method that will cover all those situations for which we do have.
So what I meant, from a pure statistical point of view, even though adaptation was not foreseen, it would still give you a way to control the type 1 error rate.
Yeah. So there are two elements. One is controlling the, and so the advantage here I'm understanding is that not only do you control it gives you the option to control your error rates in a circumstance where life has happened to you. Okay. I don't see any more questions on the Q&A poll. Are there any questions on the call? Guosheng, I'll ask you the same question I asked Franz with regards to implementation. How easy is it for the jobbing statistician to code up the methods you've described in their tool of choice?
In terms of the practical use, the method I proposed actually only depends on the Kaplan-Meier estimator in terms of handling those delayed response. And the Kaplan-Meier estimator is very easy to implement, and it's widely available in almost every statistical software. So the computation is very quick and straightforward. Well, in terms of adaptive randomization, it will be more challenging and demanding than those traditional fixed sample design, because you have to have a multidisciplinary research team and infrastructure to allow for frequent updating of the information and the timely data analysis, so that you can work with other team members together to implement such a real-time adaptive randomization. And in terms of using either equal randomization or adaptive randomization, this is still a very subtle issue. Recently there's still a lot of debating going on about whether you should use fixed randomization or adaptive randomization. If you don't use equal randomization, you can use the fixed randomization with the ratio 1:2. If you believe one treatment is better, you just assign twice as many patients in that arm than the control arm. So there's still a lot of issues being debated in recent years, but I would view it depends on the real situation. It depends on how long is the lag time to observe the response, and also it depends on whether the disease is rare or common. In terms of whether the trial has already recruited most of the patients if it's rare disease. If it's a common disease, then the number of patients in a common trial is small in comparison to the entire patient horizon. The patient horizon is the trial patients and also those patients outside of the trial. If you can get the trial finished sooner, those patients outside the trial can benefit from this drug sooner as well. So it really depends on the practical application. Depends on the nature of the disease, whether it's rare or it's common, and whether the outcome can be observed quickly. If you really have a long lag time to observe the response, then that can mitigate the advantage of AR. Also, it depends on whether you have early stopping in your trial conduct. If you have early stopping for security or futility, then that also can be can diminish the advantage of using AR. So it's very complicated issue. So there are a lot of discussions going on. You have to talk to the collaborators, talk to the team, and to get more frequent updating of the information. So it is very challenging, in trial conduct, in trial conduct.
I think that's a good warning, or a good piece of advice, that getting the technical details are one part of the fight, and the second part is making sure that it works for the context and for the whole team. I think it's also perhaps a nice implicit endorsement of the work that Franz has presented, is that it is very intuitive. And I can certainly speak to the experience we've had in the company in which I work in presenting testing procedures in that way, and our success in doing that. So that is probably a good place for us to finish the discussion, unless there are any last questions that people have either in the meeting or on the phone. Okay. In which case, all that remains for me to do is to, again, thank both of our speakers for committing the time to give these very interesting talks to both the Royal Statistical Society and to statisticians in the pharmaceutical industry and members of both groups. And to the team at the RSS who put so much work into running these sessions along with the team at PSI and have been working very hard throughout this call to make everything run smoothly. Thank you all for dialing in. The slides and the recordings from the talk will be available on the RSS website in due course, so you'll be able to follow up or share with colleagues the information that you've learned.